Okay, I was muted. Hello, everyone. Can you see my screen? I cannot see the chat. Oh, there's the chat. Oh, you can. Okay, sorry. So I just maybe I'll put this here. And am I recording? Yes. Okay, cool. So welcome to Math 1510, Deep Learning Theory and Data Science. I wanted to start today's lecture with a short reminder of what we've seen in the previous lecture. So in the previous lecture, we've seen this plot, this illustration, and we've discussed how much effort went into creating these speckles on these spheres. And in this illustration, we have these red spheres, which are the different class classifiers. Each shade of color corresponds to a different class. We have 3 classes in this case. And each small blue sphere is a feature in the last layer. And you can see here the different features. And the large blue spheres are the class means of the different features. And so if you were to average all the small spheres in a certain class, you would get the class mean, which is the large sphere. Now we've defined the within class covariance, which you can see here, which essentially measures how far away are the features from their corresponding class means. And we've defined the between class covariance, which measures the covariance of the class means. What is happening with some of your Zoom technology seems to be very strange today, I must say, very strange. Okay, and we've also defined the simplex ETF, which, what? Yeah. We've also defined the simplex ETF, which was this perfect configuration that is plotted through these green spheres. And then we've seen this animation that showed a convergent process, which we've called neural collapse. And in this convergent process, you can see how the within class variability tends to 0 as the small blue spheres tend to the large blue spheres. That's the first property, which is called NC1. The second property is that the class means converge to a simplex ETF. And so that means that the blue large spheres are converging to the green large spheres. And that means that these class means are, in some sense, perfectly angled between every pair. Every pair is creating this perfect angle. I don't know how to do it with my hands. I guess that's what we have in animation. And the third property was convergence to self-duality, which said that the class means and the classifiers converge to each other. Now we've summarized these properties here. So here you can see NC1 within class variability collapse, NC2 class means converge to a simplex ETF, NC3 convergence to self-duality, and NC4, which says that the decision of your network's classifier is equivalent to picking the class whose class mean is closest to you. So if this is a point in space and you need to assign a class to it, then all you have to do is basically look at the closest class mean and just assign the class of that class mean. So with this, I'm going to switch to my tablet because I've shown the animation I wanted to show. Let's switch to my tablet. Does anyone have any questions? Any questions?
I have a little question.
Yeah.
So the setup, just a quick review of the setup is that after you apply things, after you push the image through the layer until the very last layer, then you all of a sudden have something that can be linearly classified using these WC.
Yes, but the words linearly classified are weaker than what's actually happening, because data is linearly classifiable or linearly separable if it looks like this, right? This is a linear classifier. But if data is linearly separable, there's infinite possible linear classifiers, right? This is another linear classifier. And in a previous lecture, we've talked about how there's a very specific classifier, which is the max margin classifier, right? Which maximizes the distance to the closest point. And what neural collapse is saying is that not only is your classifier a max margin classifier, it is the most optimal max margin classifier you could ever imagine. So I will actually discuss this in a couple of lectures probably, but it's a very, very, very specific case of a linear classifier. So what you said, Neo, is correct, but it's not that that the network manages to linearly classify the data at the last layer. It's that the linear classifier is a very specific linear classifier, which satisfies a lot of simple properties, very strict geometry. The classifier satisfies very rigid geometric properties, which you wouldn't expect in general. Does this make sense?
Sounds good. I'll just follow along and then think about it more.
Okay.
Thank you.
Okay, so let me show you the empirical evidence that supports neural collapse. So in this figure, on the x-axis, you can see the epoch of training. So the epochs start from 0 all the way to 350. In the case of ImageNet, it's only until 300. There's a vertical red line which indicates the point in time, in epoch time, in which the network reaches zero training error. Zero training error means that the network has classified all the training examples correctly. Does everyone remember? Oh, there was a question in the chat. Is your background what we're supposed to get for homework 4? Huh? Oh, no, it's not. It is not. So does everyone remember what does it mean for a network to reach zero training error? So does the definition of the red line make sense? It does. Okay. Oh, there was what? Okay. And on so notice how different rows of plots correspond to different architectures that you might remember from our earlier lectures. So the first row is the VGG architecture, which we might have seen in the homeworks. The second row is a ResNet architecture, which we've definitely seen in the homework. And the third row is the DenseNet architecture, the DenseNet model. These graphs are not graphs of the test laws, Karen. I'll explain in a second what they measure. Notice that each column of figures of plots corresponds to a different data set. So we have MNIST, fashion MNIST, and so on. And the data sets are ordered in a specific manner that reflects their difficulty as we perceive it. So MNIST is a simple data set, easy to get to very good accuracy. STL and ImageNet are significantly harder. Now, within each one of these plots, we measure the quantity written here. What is this quantity, you might ask yourself? So the quantity is the trace of the within class covariance multiplied by the between class covariance, let's say inverse or pseudo inverse, depending how accurate you want to be. And there's a scalar of 1/c that you can see here. What does this quantity measure? Does anyone know? Why would we within class covariance? Yes, it is the within class covariance, yes. Yeah.
I think it also normalizes with the number of classes.
Yeah, that is correct. We're normalizing by the number of classes. Yeah, the size of the covariance, as Neo says, exactly. So let me show you a related quantity, and C is the number of eigenvalues, exactly. Wow, Neo seems like a spectral expert. Average eigenvalue size, that's exactly correct. Let me just show you a related quantity just to evoke some intuition. Imagine if we were to measure the between class covariance multiplied by the within class covariance inverse. Recall that the between class covariance is equal to M transpose, where M is a matrix whose columns contain the class means divided by C. So it's 1/c. Does this equality make sense? So all I said here was that the between class covariance is equal to 1/c M transpose, which is equal to the average of the class means minus the global mean. And I ran out of space. What is going on? Oh, okay. Let's make it smaller. Multiplied by the class means minus the global mean transpose, right? And so notice that at the bottom right, this quantity can be written as 1/c of M multiplied by sigma W, I guess it should be sigma W minus half, multiplied by M Frobenius squared. Can you decipher my horrible handwriting? This isn't, not everyone is. So this is a sigma W minus half multiplied by a means matrix M, right? Now, don't you feel like this is a very intuitive quantity? Sigma W minus half multiplied by M. Do you remember seeing such a quantity in your past? Not in the very, yeah, it's signal to noise ratio, exactly. Yeah, well, Neo is on fire today. So it is the raw thing. It is the raw thing. So basically, sigma W minus half makes sure that your within class covariance is an identity. Oh, what have I done? Oh, and the M's are just the class means after the transformation. And we're basically checking how large are the class means compared to the noise. So the class means are the signal, the within class covariance is the noise. and we're checking how large is the ratio. Does this make sense? Or is this making no sense? Somewhat makes sense. So the quantity here, which is the quantity that's actually being measured, is just the inverse of this quantity. How this Frobenius equality works out. Do you mean this last step, this step? Oh, so I have no space, but maybe I can use my words to describe this. So the first thing you do is you decompose sigma w inverse to the multiplication of 2 sigma w minus halves. So you write it as sigma w minus half times sigma w minus half. And the second thing you do is you use the cyclic property of the trace. Have you ever heard about the cyclic property of traces? It's a very useful property in life. You have not? Okay, so, okay. How about I just do this more carefully here, just to make sure that everyone understands this, because it is useful. So if you have a trace of sigma, what was it? Sigma b times sigma w, and you write it as 1 over c trace of m transpose sigma w minus half sigma w minus half. The cyclic trace of the cyclic property of the trace says that trace of AB is equal to trace of BA. So you can just cycle it around, right? And so what we're going to cycle here is the trace is going to be m transpose sigma w minus half sigma w minus half times m, right? And then there is the relation between the Frobenius norm and the trace, which says that the trace of A transpose A is equal to the Frobenius norm of A squared, right? Have you seen this? You have. And so this is equal to 1 over c times, I guess I should write sigma w minus half times m Frobenius squared. Does this make more sense now, Karen? It does. Okay. Okay. And so this quantity is, or this quantity is just the inverse of this quantity, right? And this quantity is much more pleasant to work with empirically. So that's why we measured this quantity. Now, what would you expect to happen? What you would expect to happen is the within class covariance should decrease, right? Because I've shown you animations where the within class covariance vanishes as the activations collapse to the class means. And indeed, in this plot, you can see how the within class covariance is vanishing after the normalization towards a very small value. And this happens across all the data sets and networks, with the exception of ImageNet, where it's harder to achieve small within class variability. But at the end of the day, everything is a question of how much money do you throw at the problem, in the sense that if you have a lot of compute and you do lots of hyperparameter tuning, you get to a small within class covariance. In the case of ImageNet, running lots of experiment is rather expensive. Does anyone have any questions about this plot? Any objections?
Professor?
Yeah.
I have a small question. So the within class variant, within class covariance is the noise, and then the signal is the between class. So the trace of the SW over B is the opposite of that.
Yeah.
Okay.
Yeah. And you
Sounds
don't
good.
have
Thank
to
you.
use the trace. One could use other exotic quantities like, you know, the log determinant. That's a very popular thing to use. what is a better measure of performance for networks when training error gets to 0 or decay of trace SBA? So it's actually neither of those, because in a network, what we know is that a network is so over parameterized that you can get 0 training error, right? And the fact that you get to 0 training error does not indicate really that you're going to generalize well. So the only thing that's truly indicative of generalization performance, I would say, is looking at the test error, or looking at this quantity for test data, like for the test features instead of the train features. Yeah, that's what I would say. Although there are theoretical works that try to say that the test error can be predicted from the train error and so on, but let's leave those aside for now. So the next plot has a very similar structure, except that it's showing something else on the y-axis. So here you have on the y-axis a standard deviation over the average of the norms of the classifiers or the means. So what does this mean? So imagine you take all of the classifiers, and for each one, you compute its L2 norm, right? So you get L2 norm of WC, where C goes from 1 to capital C, right? So how many numbers do we have? We have capital C numbers. And imagine that you take these capital C numbers, which in the case of MNIST would be 10, and you calculate their average, sorry, their standard deviation over the average. Why would this be an interesting quantity to measure? Does anyone have any idea, thoughts? What is written inside the norm? My handwriting is so horrible. You cannot decipher what's written inside the norm. Uh-oh. So what's written inside the norm is the L2 norm of the Cth class classifier. So WC is, oh, okay. It's hard to see the, okay, I should avoid writing there. My bad. Is this better? Okay. Yeah, so what you can see, so you can see that we're measuring the standard deviation of the average, and Amireza says this is the normalized deviation. So if the normalized deviation, what is the mean activation? What do you mean by what is the mean activation? The blue. Oh, it's the class means. Mu C. So if you measure the standard deviation over the average, it's just checking how different are the different values. So if the standard deviation is significantly smaller than the average, it means that all the quantities are approximately equal to each other. And so if you calculate the standard deviation over the average of these quantities, right, then it measures how different are the different norms of the classifiers. Does this make sense? So it measures how different are the classifier norms from each other. If the standard deviation is significantly smaller than the average, it would mean that all the classifiers have approximately equal norms. Do you remember from the visualization that we saw in the beginning that all classifiers at the end had approximately the same norm? Because all of them were approximately of equal length. Do you remember such thing? You do? That is correct. Yes. We're plotting like average and STD over the W and the mu C respectively. Maybe I can write very explicitly what's meant by standard deviation over the average. So the standard deviation is the average of the L2 norms minus the average of the L2 norms squared with a square root. Do you remember standard deviations from probability? Do you remember standard deviations? So this is the precise definition. And the average in all cases is over the C index. Is this more clear or less clear? It's more clear. Now you can repeat the same thing for the feature class means, right? And that's what's happening here in orange. And you can see how the standard deviation over the average converges to a very small value in all cases, which indicates that the classifiers and the feature class means converge to being equinorm. Equinorm means equal norms. So yes, if you combine all the plots together, that is what they would show. That is correct. So the next plot shows the standard deviation of the cosine. What is a cosine? So we define the cosine of class, let's say C and C prime, to be, for example, WC prime inner product with WC divided by the norm of WC and divided by the norm of WC prime. So this is just the inner product after you normalize the vectors to unit norm, right? And so this cosine is going to be a number that measures the angle between the two vectors. Now, our prediction is that the cosines should be equal to each other, right? Because we predict that all angles converge to being equal. So what we're measuring is the standard deviation of the cosines. And what you can see is that the standard deviation of the cosines decreases to 0. In some cases, it decreases to a better value, in some cases to a slightly worse value. But in all cases, it's less than 0.1, which means that the standard deviation is very small. So this proves that the angles are equal. The next plot shows that the angles converge to the optimal value. So the optimal value is the cosine of C and C prime should converge to -1 over C minus 1 for this to be a simplex ETF. Why is the performance on ImageNet the worst in all plots? Because basically you are in each one of these experiments, right? This experiment is the result of many, many experiments that tried many hyperparameters and looked at the network that performed best on test data. So I'm showing you the experiments that performed best on test data. Now, what is implied is that we train a bunch of different networks and chose the best one. In the case of CIFAR, it's easy to run thousands of experiments. In the case of ImageNet, it's very costly to run thousands of experiments. So we ran what was within our budget. Yeah, it's very costly, unfortunately. So that's one explanation. Another explanation could be that in the case of ImageNet, you have a large number of classes. Maybe that's somehow important for the phenomenon, but I don't think so. So here on the y-axis, I'm showing you the average over the shifted cosines. So Why is there a lot of jumping in some plots as they tend to 0? That I cannot answer. That I cannot answer. Jumping, you mean like the plot is not very, like these type of things or these type of things? Yeah. Like in STL ResNet. Oh, I see. Like these type of things. Yeah, I don't have a good explanation, but we're dealing with a high dimensional non-convex optimization problem. The fact that you can see a trend is a miracle, right? So I'm willing to see a trend with a lot of jumping if at the end of the day there's still some trend. I'm not aware of an explanation for why there are jumps, but you can see these jumps in different measurements you would make in deep learning unrelated to neural collapse. Like you might see jumps in train error, in test error, and so on. I guess this is an unsatisfactory answer though. I guess it's unsatisfactory. So what this plot shows is the average shifted cosine in absolute value. So the average shifted cosine is defined to be the cosine between the two different classes minus this quantity, which is the optimal angle, absolute value average over C and C prime not equal to C. So we're just averaging how far away are the cosines from what we'd predict should be the optimal value. Does this make sense? Does anyone have any questions? In case of ImageNet, does not converge plots. You're dissatisfied with the convergence of ImageNet. I mean, in this case, it's actually not bad. You're still dissatisfied.
My question is that if the final asymptotic value, does it have any relation is there any relation between the complexity of the data? I mean, I see that MNIST has a really good performance and it converges to ETF in all these plots. I mean, it satisfies all the NC properties, but the ImageNet on all the plots, it does not converge to the desired properties. I'm thinking that maybe those assumptions about neural collapse does not hold for ImageNet or some data sets.
I mean, it's possible, but if you count how many data sets, 1, 2, 3, 4, 5, 6, 7 data sets, right? In this case, we ran experiments optimizing over, so there's different, okay, let me say it this way. Another thing you might ask yourself is when does neural collapse occur, right? Because it's possible that under certain condition it occurs, under certain condition it does not occur. And so the bigger question is when does it occur? And can we show that it does not occur under certain cases? And I will actually show different follow-up works that derive several cases under which neural collapse occurs. And I think based on those, you might have an intuition for why it's harder to achieve it in the case of ImageNet. At this point, I agree that the plots are worse for ImageNet, but there's two possible reasons for that. One is that we didn't spend enough money. Another is that the phenomenon does not actually occur there, right?
Yeah.
And I think it might become clear in the following lectures under which conditions you might expect to see these, okay? What kind of conditions would induce neural collapse? So Karen asks, which color on the graphs does the bottom expression correspond to? So Notice that in this expression, we're calculating cosines of a pair of classes, right? The cosine is the inner product of two normalized vectors. So if you take two classifiers, then you would get the orange curves. If you take two class means, you would get the blue curves. I can write it very explicitly. So in the case of the classifiers, the cosine would be WC inner product with WC prime divided by their L2 norm, WC L2 norm, WC prime L2 norm. Here you have an inner product minus 1 over C minus 1, absolute value, average over C not equal to C prime. So this is the orange curve. Okay. And the same could be written for the class means, in which case you get the blue curves. Okay, so this plot is very simple. All it measures is the self-duality. What is self-duality? Self-duality is W minus M, W transpose minus M, where we're dividing by the Frobenius norm of each matrix. So we're normalizing it to a unit Frobenius norm, and then we're seeing how close are these matrices. And you can see how in most cases you get very small self-duality. You can see how in ImageNet you get small self-duality for VGG. Amireza, are you satisfied with this number, or is it too high? Thumbs up or thumbs down? Are you convinced?
Yeah. I know it's good, yeah.
Here it's good, okay. So here it's good. Here I would say it's slightly worse. Here it's slightly worse. So here I guess it would not satisfy everyone. Okay, so this plot shows that the classifiers converge to the class means as training progresses. And the final plot shows the mismatch between the classifier decision of the network and the nearest class center algorithm. So the nearest class center algorithm would take the last layer features and calculate which class is closest in terms of class mean to that feature. So you take a certain H and you look for which class, let's say this is one class mean and this is another class mean and this is another. So you say, okay, this is mu C, H is closest to it, therefore H belongs to class C, right? This is one way of predicting the class. Another way of predicting the class is just calculating, the prediction of the network based on the weights and the biases. And what this plot shows is how many times is there a mismatch between these two predictions. So how many times do these predictions don't align? And you can see that basically very quickly you converge to full alignment between the two approaches. You can see in many cases very close to perfect agreement. Is it clear the difference between the nearest class center and the prediction of the network? Is it clear that the prediction of the network relies on the classifier weights, whereas the prediction of the nearest class center does not rely on the classifier weights? So Neo says, if you have neural collapse and you have a lot of training, you can just resort to nearest class center because it might be faster and take less computing power. It actually won't be faster because the computational complexity would be equivalent and it would not take less computing power. But the point of this is to show you that the classification process is not actually like an arbitrary linear classifier. It's a very, very specific linear classifier that you have. A very specific linear classifier. which is related to this nearest class center. Okay, so if you remember, oh, let me show you this first. So this table shows you how large is the test, how big is the test accuracy at 0 error compared to how large is it at the last epoch for various architectures. So if you remember, in all the plots, we had this line, this vertical line, and this vertical line indicated the place where you have 0 training error. 0 training error, right? So this was epoch, this was 0 training error. So you might ask yourself, how much performance improvement do we get by training after 0 training error towards 0 training loss? Is that a reasonable question to ask in your opinion? It is a reasonable question. Okay. And this continuation of training past 0 error towards 0 loss, we call it the terminal phase of training. Terminal phase of training. All the training that is done after you've hit 0 error. And what you can see here is that in many of the cases, in most cases, you actually get improvement to your accuracy. So for example, here you get, if you're at 0 error, your error is 94.64. If you train for more epochs after 0 training error, you get to 95.7. And these improvements are actually quite significant. It might look like a small improvement, but when you're dealing with this type of problems, any percent that you have is quite significant. And so overall, you can see that the terminal phase of training, in fact, improves your test error. I have no explanation for the exceptions, except one must run more experiments. If you run enough experiments, it seems to hold. It's very hard to explain phenomena on a specific data set and network combination, right? Imagine trying to explain why doesn't this work for a DenseNet image. It's very hard, right? Very hard. So another property that we found of neural collapse is related to adversarial examples. So let me remind you what adversarial examples are. So at this point, you've already attacked a network in your homework, so you're probably experts on adversarial attacks, expert attackers. But still, maybe I should remind you what it is. So imagine you take an image of a beautiful panda, and imagine that the network classifies this as being a beautiful panda. And then imagine you add a small perturbation, which is small because you multiply it by a small scalar. And this small perturbation does not change the image in a manner that is visible to the naked eye. But this small adversarial perturbation manages to completely fool the network and think that it is a gibbon with 99.3% confidence, right? Now, one of the formulations that we saw in the lecture on adversarial examples was the following formulation, which said that given an image XIC, so it's the ith example in the CIF class, so this is this image, right? We're interested in finding a perturbation A, which is the noise, so that the predicted class C hat of this perturbed image is not equal to the true class C. And our goal is to find a perturbation that would minimize some norm, right? For example, the L2 norm. So you want to find a small perturbation. And we've seen in the lecture this DeepFool algorithm. Does anyone remember an algorithm by the name of DeepFool? We have forgotten the algorithm. Okay, well, such an algorithm exists. And this is an algorithm that allows you to attack. I guess you guys attacked with PGD, right? So Reza asks, what is the measure of confidence here? Is it the distance to the borders of Renoir diagrams? The measure of confidence here is most likely the softmax probabilities. So the softmax probabilities assign a probability to each class. The network believes that this is a gibbon with 93%. Now, in this experiment, what we did was measure how robust is a network to adversarial examples as you train the network post zero training error towards zero loss. So at this point, hopefully I've convinced you that during this time, neural collapse happens, right? You converge to this optimal configuration. And what you can see is that as you converge to neural collapse, in most cases, you can see how there is a quite significant improvement to the adversarial robustness. So when we write here robustness, what do we mean? Robustness is basically how much L2 norm do you need to add to your image in order to confuse the image. So the more norm, the bigger the perturbation that is required, the more robust the network is, right? And so in most cases, you can see how there's quite a significant amount of adversarial robustness that is achieved by converging to neural collapse. Does anyone have any questions about this experiment? No questions. Okay. What makes I have no tools to answer questions about what makes a particular combination particularly bad. It's a guessing game, right? It's a guessing game. So how do you measure robustness? So let me make it very explicit. Robustness is defined to be the average of AI L2 norm over XI L2 norm. AI is the perturbation for the ith example, and Xi is the norm of the ith example. So you're checking how large of a perturbation do you need to adversarially attack the network on a certain image. So the bigger the perturbation required, the more robust the network. Does this answer the question? Okay. So imagine, Karen is asking what makes STL with ResNet particularly bad. Does anyone have any hypothesis? Let's try and brainstorm, like what could possibly be an explanation? I'm trying to, by brainstorming, show you that it's very hard to find an explanation for most of these things, right? U of T Wi-Fi instability. This was not run on U of T clusters. So such Wi-Fi instability would not harm the experiments. Unless you mean there's currently a U of T Wi-Fi instability. In which case, I misunderstood you. Yeah, so it's very hard to find explanations for outliers. Does it have any relation to the structure of the data set? So if it had any relation to the data set, you wouldn't get beautiful plots for the other networks, right? So it can't be the data set. And it also can't be the network because, it can't be the data set because other data sets Yeah, because other networks show good performance. It cannot be the network because other data sets show good performance. So it's unclear what it is. In my opinion, it's just a question of how much patience do you have? How much hyperparameter tuning do you do? How much money and patience do you have? If you do the optimization very thoroughly, we have a conjecture. Do you think inserting adversarial examples during training can speed up the rate at which neural collapse occurs? Is a beautiful research question that I have no answer to. Do you think inserting adversarial example during training can speed up the rate at which neural collapse occurs? Yeah, I don't know. It's a beautiful question. I don't know.
How consistent were these graphs over multiple runs with different sort of like random initializations, if that's what you did?
So what we did was actually we chose a grid of learning rates. Initially, it was like 100 learning rates, but then we settled down on 25 learning rates, and we ran the experiments on all of these learning rates. And what we decided is that we don't actually care what happens on networks that are performing poorly, because our goal is to try and characterize what is happening in networks that are performing well, because it sounds like a simpler question that has more chance of being resolvable. Does that make sense?
Well, I meant in terms of weight initialization.
Yeah.
I'm not sure if that
Yeah, so
addresses.
we ran just one experiment with each learning rate.
I see.
There might be a certain aspect, there might be a certain variation in the experiments if you repeat the same experiment with various learning rates. So New is suggesting that I should get a part-time job at Hollywood to be able to fund more experiments. That is a good idea, but I think even that would not be enough. I don't think that would cover it, actually. You do realize that running experiments on, like a state-of-the-art NLP architecture requires tens of millions of dollars to train. So this is not state-of-the-art NLP, but this is what is required. You know, you need like infinite GPUs, I think, to do experiments on bigger data sets. So on ImageNet, it's more reasonable, but it's I don't think Hollywood would be able to fund it. Yes. Okay, so to summarize, we've seen that canonical deep nets and data sets show neural collapse, and we've seen the properties of neural collapse. And the natural question to ask is, why does neural collapse occur? Or to Amireza, it would be, why does it not occur in certain cases, right? So with this, we're ready to go to the next lecture. The next lecture is called Neural Collapse Optimality. So here's again a summary of neural collapse, but I feel like I've mentioned this one times too many in this lecture, so I'll just skip the summary. So recall that in these experiments, we were looking basically for the most part at the last layer classifier, W, and the last layer features, which we denoted by HIC, sometimes HIC capital L. Now, notice that this notation is hiding something. It's hiding the fact that the HIC L, the last layer features, are actually a function of your input images and a bunch of layers, a bunch of parameters of layers prior to the last layer. So I think the mental image that you should have is the following. Let's say this is a block. This is the last layer classifier. And so the last layer classifier makes a prediction based on the features which we denote by HICL, right? But these features are a result of a very complicated feature engineering process, right? This is feature extraction. So there's many different layers prior to the last one that are creating the last layer features, right? And at the beginning, we had the XIC, which are the pixels. And when you train your network, what you're doing is usually called feature engineering, right? So what does it mean to do feature engineering? In some sense, it means to be optimizing these H's, right? In some sense. So imagine the following slogan. The slogan says, neural collapse is the preferred end state of a successful feature engineering. So if your training was successful, neural collapse would emerge. But the question is why? Why would neural collapse emerge for every successful feature engineering exercise? So to answer that, we go back in time to the seminal paper of Claude Shannon. Are there any Claude Shannon fans in the audience? I know at least, yeah, at least one. Yes. Lots of Claude Shannon fans. Now, in this paper, Claude Shannon considered the following problem. Imagine that you have a certain transmitter that transmits code words. Code words which are denoted by mu gamma, and mu gamma is restricted to be in a set of mu seeds. So basically you have capital C vectors, right? Mu C from 1 to capital C. Now imagine that we're choosing gamma with a uniform distribution. So you pick randomly the gamma. Now this transmitter is transmitting, so the transmitter is picking a certain mu gamma, and then this mu gamma is being transmitted, and due to this transmission process, there is some noise being added on top of this code word. And this noisy version, this is transmitter, this is receiver. This noisy mu gamma plus z is obtained by a receiver, and the receiver is interested in finding some gamma hat, trying to figure out which of the original code words was transmitted on the channel. Does this sound like a reasonably important problem in real life? It does, right? It does. Now, we're assuming here that the noise is what's called white Gaussian noise, ID white Gaussian noise. Now, imagine that the receiver is lazy and the receiver restricts themselves to a linear decoder with certain weights and biases. So that means that gamma hat is going to be just argmax over the different possible C's of WC inner product with H plus BC. Does this look like a reasonable decoding step to you? Is this reasonable? It's just an affine transform, right? It's equivalent to predicting gamma hat based on an affine transform. Reasonable, right? Now, what is the goal in this linear decoding over a Gaussian channel? The goal is to be able to design the weights, which are denoted by WC, the biases, which are denoted by BC, and the code words, which are denoted by mu C, right? Because these are all the parameters of the problem. Now, we're going to constrain ourselves to a sphere, so we're going to assume that the code words have a limited L2 norm. And you can make up justifications for why that is needed in real life. Does the setting make sense? Does the problem make sense? So this is the problem that Shannon was interested in. Now, here's a question. A 1 minute summary. A 1 minute summary of what? Of the problem? Losing a big picture view. Yeah, so, okay, so the question is, we saw that neural collapse emerges in different feature engineering exercises. When you train a network, you get neural collapse, right? And the question is, why does neural collapse emerge? Why? Can you give like a reasonable explanation, right? So in order to explain one point of view, I'm explaining how a person from information theory with an information theory background would look at this problem. So a problem from a person, sorry, with information theory background might think of this problem that I'm describing here. So this problem assumes that you have a certain transmitter that is transmitting signals over a Gaussian channel and a decoder that's trying to understand what is the signal that is being transmitted. Now, at this point, it's not quite clear what is the relation between this and what we're talking about earlier with neural collapse, right? It's not particularly clear, but I'll explain that in the next slide. For now, I'm trying to make sure that you understand this, this question, this setting. Is the problem making sense? So the answer that, so Karen asked, why would you want the norm of mu-c to be less than 1? And indeed, the answer by Justin is correct, that it's like a power constraint. I'm not proficient enough in this area to explain what a power constraint is in the context of information theory, but I've read the same type of claims in papers. So here's a question to you. How would you define, so what's missing from this problem here? Is there something that's missing in my description of the problem? Is there something that I did not specify and perhaps should be specified? So what's missing here is, how do you define, you're probably working with a probability thing, not deterministic. Yes, but that's not quite what I meant. So one thing that's missing here is, how do you define what's a good set of weights, biases, and code words? You need some type of a criterion, right? So consider the following criterion. This criterion is called a large deviation error exponent. So what it says is, what is the probability of the decoder finding a gamma hat which is not equal to the original gamma? So in simple words, this means decoder decodes incorrectly, right? And what we do is we look at the probability and we apply a log and multiply by sigma squared, which might look a bit strange. And we claim that this is the correct criterion to be looking at in the limit of sigma going to 0. So in the limit when your H's are distributed around these mu gammas with a variance, with a noise with a vanishing variance. And this is the limit that we care about. Now, does anyone see the relation between this problem and what we're talking about in deep networks? I think that's what Nia was hinting at, that this part is not clear. So what is the relation between this and deep learning?
Would it be like the idea of the adversarial example? Like the noise, we're adding noise.
Not quite, because in this case, the noise is not adversarial, right? But essentially, what we're doing, but we will see, as you propose, we will see that as well in a few slides. So we will see what you just said in a few slides. So the idea here is that imagine that you have a very, very powerful feature extraction process that is capable of representing any H's that you might have, but it's only strong enough to find the means. It cannot change the variance. So basically, your feature engineering can design the mu-Cs, and you can also train the classifiers W, and you can also train the biases, right? But you don't have enough parameters in order to choose the perturbations from the means, right? So imagine that under such setting, you ask yourself, what would be the optimal means, weights, and biases? It's basically what one might call, it's godlike feature engineering. Godlike feature engineering in the sense that you are able to pick the classifiers, the biases, and the feature class means. Does this make sense, or it does not make sense? So basically, the mu gamma are analogous to the class means. The H's are the features. These WC and BC are the classifier, right? And these Z are the perturbation of the features from their corresponding class B. And essentially, we're assuming that the perturbations are Gaussian. Does this make more sense, or does this make less sense? Amireza says samples are created from mu-C added with noise. That is correct, yes. It's equivalent to less sense a bit. Are the mu-C's average? The mu-C's in this specific case are analogous to the class means. So they are averages. But in the network, they were calculated as averages. In this case, you can think of it as a class mean that you can steer. What do you mean by seems like they're just inputs? It's not very clear to me. So the problem in this specific case is to design the weights, the biases, and the code words. It's analogous to training a network. When you're training a network, you're trying to find the optimal classifiers, biases, and all the weights of all the layers, right? Maybe I can define it more clearly here. The problem is defined here. This is the problem. The problem is for you to find optimal, I guess this should be M, not H. Find the optimal weights, the optimal biases, and the optimal class means that would minimize this large deviation exponent error. This large deviation exponent error is the probability of misclassification as your deviations tend to 0. Okay, it seems like it still does not make sense. Okay, how about we try another thing? Here's an alternative setting that maybe Gina would like. Let's appeal to Gina's taste. So Gina proposed the following setting. Gina said, imagine you have a set of class means, right? And to those class means, you're adding some perturbation, which is an adversarial perturbation because it is bounded by, let's say, an L2 norm, right? So this is analogous to an adversarial example. And then imagine that you have the ability to design the last layer classifier, bias, and also the code words. And again, you are bounded to class means which are which have less than one L2 norm. Is this, Gina, the problem that you had in mind? It is somewhat. Not quite. Does anyone like this problem more, or is this even more confusing? The only thing that changed was that here, instead of assuming that the perturbations are normal 0i with a covariance sigma or epsilon, whatever it was, here we're assuming that A has a bounded L2 norm. So Amireza, being an expert in information theory, says these results come from asymptotical theorems in information theory. So in our framework, should we take a limit of sample dimension to infinity? So that's very, very precise what you're saying. In this specific case, we do not take the sample dimension to infinity, Amireza. But that's a very good comment. It's a very good comment. That is a very good comment. So why is this question, or why is this problem interesting? Because one can actually prove, let me explain this. In this case of adversarial robustness, what you might care about is trying to maximize the adversarial radius. The adversarial radius is the minimal L2 norm that is required in order to cause a misclassification. So you would like to maximize the misclassification. You would like to maximize the epsilon that would cause a misclassification, right? This quantity is basically robustness, because alpha measures what is the minimal epsilon that would create a misclassification, right? And what you would like to do is increase that epsilon as much as possible. Does this make sense? So big H is, it should be M. M is the matrix of the class means. Is it because we normalized mu C's? I don't understand the question. Is it because we normalized the class means? Oh, yeah. You're correct, Amireza. Yeah. Or you can think of it as another measure of robustness. But you're correct what you said, yeah. So why is any of this interesting? Because you can show that the optimal adversarial robustness is achieved if you choose your classifier to be a simplex ETF, and if you choose all your features or your class means to be a simplex ETF as well. So basically, if you are trying to optimize your adversarial robustness, then you should tend to neural collapse. And you can show an analogous theorem for the previous setting we were discussing that you seem to like less. So in this setting, you can also show that if you're trying to optimize this large deviation error exponent, which is basically misclassification under very small noise levels, then the optimal performance is going to be achieved when your classifier is equal to a simplex ETF and your class means are equal to a simplex ETF. So what this implies is that the reason neural collapse is the preferred end state of feature engineering is because the simplex ETF is the optimal configuration for let's ignore this sentence, in terms of adversarial and Gaussian noise. It is the optimal thing you can do. So maybe I can show you a very simple illustration for why is this optimal. So simplex ETF looks like this, right? Imagine if you had something like this. This would not be optimal in terms of adversarial robustness, right? I think Amireza even said this in the previous lecture, just intuitively. Because here you would be able to misclassify, very easily, right? Very small perturbation. Whereas here you would need a larger perturbation. Does this make sense? So why do we assume that there is a norm constraint on the class means? Because if you don't put a norm constraint on the class means, then it doesn't make sense, right? You want to assume everything is restricted in terms of the class means, and then compare different configurations. Does anyone have any questions? The engineered features are so the code words correspond to the class means of the engineered features. Class means of the engineered features. Essentially, the idea is that you would like to show that neural collapse is the solution under certain settings, right? And what I'm showing you here is one case in which simplex ETF is optimal. It is optimal in terms of adversarial robustness and in terms of resistance to Gaussian noise if you assume that your SGD training is able to steer the class means. So as Jack says, engineering is steering class means to a simplex ETF. That is a beautiful sentence. Beautiful sentence. So I would just add to this beautiful sentence is that engineering is steering class means to simplex ETF and classifiers to simplex ETF, right? Do you agree? Okay. Okay. Oh, Amireza asked, I don't get the intuition of limiting sigma to 0. So that intuition is very simple. Do you remember that in neural collapse, we saw that the features are collapsing to their corresponding class means? Do you remember that?
Yes, I can remember.
So with that in mind, doesn't it make perfect sense to assume that your variation is tending to 0? Because the reason why you might assume, where is this? Here. This thing is measuring the variation of the features around the class means.
So you're saying that ETF corresponds to the case that sigma is equal to 0?
No, it tends to 0. Simplex ETF is optimal in terms of the large deviation error exponent, and the large deviation error exponent is defined once sigma tends to 0. It's maybe I can draw a picture to explain. So here's the picture. Imagine you have this thing and this thing and this thing. So this is mu1, mu2, mu3. And what we're doing is we're assuming that there is a very small amount of noise. And so the features are highly concentrated around the class means. And what we're saying is under certain very small probability, there's going to be a misclassification, right? What would be the optimal class mean and classifiers that would minimize the probability of misclassification? Does this answer your question, or I still sense lack of satisfaction? Yeah, they do tend to the class means because of the NC1 property, which is that the activations collapse to the class means.
Now I understand. Yeah. And I have another question. In information theory, there is an approach that called achievability, and they propose some coding methods that we can achieve this optimal error exponent. Is there any similar technique in this framework that systematically achieves this optimal error exponent here?
So what we're showing is that the deep network training naturally converges to a configuration that is optimal. In information theory, they design these because they're interested in finding robust codes, right? Or codes that perform well on Gaussian channels. What we're seeing here is that the network naturally converges to such solutions. So the claim is that the network converges to a solution which is optimal in terms of robustness and Gaussian noise. But there's no explanation for why does it converge there, right? It's just that it converges to a good place. The place to which it converges to is good. Why does it converge there? That's a good question. So it's different than in information theory, right? In information theory, one would construct this purposefully, let's say.
And I have another question. Can I ask?
Yeah.
From the figures in your last slides, you showed that after training, error becomes 0. We should wait until we can see the neural collapse occurs. So if we want our network become robust against these adversarial attacks, we should proceed with training the network even the training error is 0. Or are there similar techniques that apply this perspective?
No, but it's a good research question, but no one has done that yet. I think that the proper a proper experiment would be to compare how good is this adversarial robustness to adversarial robustness you get from other, from adversarial training, for example, right? But I'm not aware of anyone who did this. We published this a few months ago, so I don't think anyone had time to do that yet. So Karen says, when we take sigma to 0, isn't it an unnatural operation that we're assuming it to be? Yeah, it's kind of circular, right? That's what you're saying? Yeah, you're correct, you're correct. But if you've reached a point where where this happened, where the features are close to the class means, right? from that point, you can prove that the ETF is the optimal solution for the class means and the classifiers. I agree that it's not, completely resolving the, it's a claim. It's not a perfect claim, right? I agree with that. Exactly. The point is, what can we assume to make sure collapse happens? And that will be a topic of the beginning of the next lecture, actually. So to summarize this, what we've seen is that canonical datasets and deep nets exhibit neural collapse. And we've seen that neural collapse is optimal under Gaussian noise and under adversarial noise. So with this, we're ready to move to the next slide, which is called neural collapse relation to max margin and LDA. So the point of this topic is to explain how is neural collapse related to the previous topics that we've seen in the lectures, and also how is it related to, does anyone know what? How is this related to, besides the lectures, it's related to, what is there in life except lectures? Homework 5, that is correct. Yes, that is correct. So here's again a reminder of neural collapse. And if you remember, a couple of lectures ago, we discussed a paper by Webb and Low, which was called the Optimized Internal Representations of Multilayer Classifier Networks Performs Nonlinear Discriminant Analysis. Does anyone remember such a paper? Okay, we do remember this paper. Now, in that paper, what Webb and Low showed was that if you have a network which is trained with mean squared error, and if you assume that all the features are fixed, there is no feature engineering, you know, all the previous to last layers are frozen, then the optimal classifier and weights, the optimal classifier weights and biases are given by these expressions. Does anyone recognize these expressions, or is this the first time you've seen them? So these expressions are meant to evoke a connection between deep networks and linear discriminant analysis. So you can see how the Ceph class classifier is equal to the class means minus the global mean multiplied by the between class covariance plus the within class covariance inverse. So in fact, we actually derived this a few lectures ago. This very equation was derived in front of your eyes. Does anyone remember this being derived? You do? Okay. And also was derived in front of your eyes was the optimal bias, which is equal to 1 over c multiplied by a once vector minus this expression. So it's mu c minus mu g, the between class covariance plus the within class covariance inverse multiplied by the global mean transpose. Now, one could ask themselves, what is the relation between this result by Webb and Low and neural collapse? Can one ask themselves that? One can. And does anyone have any ideas? What is the relation? Is there a relation? Let us think. Sink in a deep ponderment. Is ponderment even a word? The optimal classifiers were predicted to be the same in both cases. No. So you say the optimal classifiers were predicted to be the same in both cases, but in the case of neural collapse, we didn't. Not quite. So one thing you could do is, if you remember, one of the properties of neural collapse. So in this case, the Webb and Lowe are assuming that there is no feature engineering, right? Now, if there is no feature engineering, it means that the features HIC are fixed. So what would be a reasonable place to fix HIC? If you were to choose, you know, HIC to be equal to something, what would you choose them to be? Mu C, says Amireza. What an interesting answer. So Amireza is basically saying, let us assume that the features have a 0 within class covariance. Is that fair to say? It is fair to say, yes. So in that case, one could ask themselves, what would happen with the optimal classifier, right? So let us try. If one plugs the assumption that the within class covariance is 0, then the optimal classifier becomes sigma B plus 0 pseudo inverse times mu C minus mu G, right? Does this look correct? Now, let us write this equation by stacking all of the classifiers next to each other into a matrix W. And let us also, so sigma B pseudo inverse multiplied, and then I'm going to stack all of this mu C minus mu G, which is supposed to be a G, into a matrix M, right? Does this look reasonable? Now, if we use here the definition of sigma between, so sigma between is equal to 1 over CM transpose, right? So we get M transpose inverse M. It's possible the scalar is incorrect. Is the scalar correct? Yeah, it's correct. Now, this thing, does this look to you like neural collapse, or does it not? New things, got it. New says duality. What about duality?
Can we say that they converge, W and M converge in Frobenius norm? That was one of the neural collapse properties.
Yeah.
And actually, the thing on the right-hand side is the M over Frobenius norm of M.
But it's not the Frobenius norm. M transpose is a matrix, right?
Yes.
In fact, this has a name. This is called M pseudo inverse. If you heard about pseudo inverses in your life, have you seen pseudo inverses? If you don't like pseudo inverses, I can just delete this. So here's a clue. Does anyone know how do the singular values of M pseudo inverse look like? So if we do M equal to U S V transpose, this is the singular value decomposition, SVD decomposition of M, right? How is the what is going to be M pseudo inverse? What is a pseudo-inverse is a good question. So pseudo-inverse is when you, I guess one way to define pseudo-inverse is U as pseudo-inverse V transpose. So it's basically when you invert the non-zero singular values, as Jim Shaw beautifully says. So you take a matrix, you do the singular value decomposition, and then you invert the non-zero singular values. Does that make sense? Karen, does it sound reasonable? It's kind of like an inverse, except that it's not an inverse because you can define this for non-square matrices. Because you can do singular value decomposition on non-square matrices. So if we use the singular value decomposition, then we can write this as something like, let's say, UI VI transpose and 1 over SI, where you're summing over I. So this is another way of writing the singular value decomposition. So you can see this from this equation. So here you can write this as sum over UI VI transpose 1 over SI. Does this look correct? Now, here's the question. If we look at this singular value decomposition, can we say that the classifier is an ETF or not an ETF? So what was one of the ways to determine if a matrix is an ETF? All 1, says Neo. That is correct. So if all the singular values of a matrix are 1, then the matrix can be an ETF. So if it has C-1 singular values which are equal. So in this case, you have 1 over S, and S can be anything. It's just the singular values of the class means. So what this means is that the optimal classifier, even if sigma W is equal to 0, is not an ETF. So you do not get neural collapse even if the within class covariance is 0. So what you can do, however, is you can assume 2 things. So you can assume NC1, which means that this within class covariance is 0, and you can assume that the class means are a simplex ETF. If that is the case, then you can actually prove that the optimal classifier is a simplex ETF. So if you impose these 2 properties, which is that the within class covariance is 0, and that the class means are a simplex ETF, you can prove that the classifier is a simplex ETF as well. But assuming just that the within class covariance is 0 is not enough. You can almost see the proof in the previous slide. If M has singular values, if M is a simplex ETF, then all of its singular values are equal to 1. And therefore, this is just 1 over 1, for example, right? And it just becomes 1. So there remain 1 here, and therefore W is a sum of singular values which are 1 multiplied by UV transpose. Does this make any sense? It seems like if a person is not familiar with singular values, this might be a lot of information coming at once. So I guess this would make less sense. But the point of this is to connect this to what we've previously seen. So previously we've seen the idea of the idea of linear discriminant analysis and how something similar to linear discriminant analysis emerges at the top layer. And what I'm saying here is that neural collapse is a more specific case of just assuming that you have an optimal classifier at the top layer. It's a very specific case that emerges if you have within class covariance 0 and if the means are the simplex ETF. So another way to think about it is that if you're not doing any feature engineering, then there's no way for your theorem to come up with the idea that the features would tend to a simplex ETF, right? If you would take into account the feature engineering, then the features and the class means would be able to move, and only then they would converge to a simplex ETF. What about NC3 and NC4? So NC3 emerges from this fact because this is saying that W transpose is a simplex ETF, which is equal to M. And NC4 can be proven based on NC1, 2, and 3. But I would prefer not to go into the details of the proof because it seems like we're too, maybe it's a bit too hairy. The next thing that we've seen in the course is the implicit bias of gradient descent on separable data. Do you recognize this? A max margin classifier. A max margin classifier emerges if your data is linearly separable, right? So if you have something like this and something like this, right? Then your data is linearly separable and gradient descent is going to converge to a max margin classifier. Now, what is the relation between the max margin classifier and neural collapse? Let me draw this for you, okay? This is a drawing. This is neural collapse. This is max margin. What is the difference between the two?
Would it be that max margin or neural collapse has the same margin between all the points?
Beautiful, Gina. Yes, that is correct. Wow. I feel like Gina might have, did you do homework 5? This is even more beautiful then. Wow, amazing. So what Gina is predicting is this plot. So in this plot, I'm showing you the margins of different examples for different epochs, okay? So here you can see the margin of class 1 and 2 and the margin of class 1 and 3. So let me remind you, when I say margin of class 1 and 2, I mean something like HIC, inner product with WC minus WC prime, inner product like this, right? And in this specific case, the first class is 1, so this is 1, and the second class is 2. And on the y-axis, I'm showing you another margin, which is HI1 W1 minus W3, right? What do you see? You see that for the largest epoch, which is epoch 350, the margins of all the examples are approximately equal. They're concentrated, right, around 10. And you can see that the margin for the pair of classes 1 and 2 is equal to the margin of a pair of classes 1 and 3, right? Why is it equal? Because they're approximately equal to 10. This line is the identity diagonal. The arrow means nothing. The arrow means nothing. It means something, but I don't want to get into it. It's too complicated. Ignore the errors. So what you can see here is that, as Gina has beautifully predicted, the margins indeed are all equal to each other. So how did Gina make such a prediction? By looking at this picture, right? In this picture, you can see how in the case of max margin, there is an example which is the closest to the decision boundary, and there is another example which is closest to the decision boundary. Trivia time. How are these examples called? What is the name people like calling them? What would be a name for them? If you had to give them a name. Support vectors, yes. SVM experts are sitting in this crowd. Jim Shaw, SVM experts. Yeah, these are called support vectors. Why are they called support vectors? Because they're kind of supporting the classifier, right? You can almost see a person there, like pushing away the classifier from them. Do you see that person pushing away the classifier? You do? Okay. And in the other case of neural collapse, you can see how all of these examples are equally close to the separating hyperplane, right? And so that's what made Gina predict that all examples in the data set are in fact support vectors. Okay. Now, we actually can show that if you assume that the data is linearly separable, which is something that was assumed in the original max margin work, and if you assume that there is a cross entropy loss or exponential loss, whichever you prefer, and if you assume that you have gradient descent with small enough step size, so these probably all of you by now have memorized these conditions because of problem set 1, right? And if you assume that there is no bias, because bias complicates life. So all of these are just assumptions about that were done in the original work, then you can prove that the classifier tends to the solution of this problem. So it's a max margin classifier. This is equivalent to saying max margin classifier in a multi-class setting. Okay, you can see here, this is the margin, right? Now, one can show that if you add the extra assumption, oh, there is a question. Relative size of support vector with respect to sample size increases monotonically as t increases and converges to 1 due to neural collapse, right? Yes, 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 yes. That is correct. Yes, yes. That is correct. That is correct. So you can actually add to this set of assumptions that were assumed in the original max margin work, you can add the assumption that you have within class variability equal to 0, and that the features are the simplex ETF. And under such assumptions, you can prove again that the classifier tends to a simplex ETF. So in simple words, what does this theorem mean? If you have a, let's say, something like this, right? Then you converge to a max margin classifier. But if you assume that your data is sitting on the vertices of a simplex ETF, then you can prove that the max margin classifier is also a simplex ETF. So under the case where you're allowed to optimize your features and to choose the optimal features, your classifier is going to converge to a max margin classifier, which is also a simplex ETF. So one way to think about this theorem is that it boosts the original theorem in that it says that if you inject extra assumptions, which are correct assumptions, you get extra properties about the classifier, which are also correct properties. So what I'm showing here is that If you look at the nitty-gritty of the proof by the max margin people, then you can see how their proof is basically assuming that there is a set of support vectors. So you can see it here, support vectors. And essentially, the underlying idea is that the max margin is always defined with respect to support vectors. But as Gina has noted, in this case of neural collapse, all examples are in fact support vectors. So it shows to you, hopefully, the very clear relation between neural collapse and max margin. Neural collapse is the maxiest max margin one can achieve, if maxiest were even a word. Okay, so we're out of time. So what we've seen is, again, that deep nets and canonical data sets exhibit neural collapse, and that neural collapse is emerging as a special case of nonlinear discriminant analysis and max margin. It's a special case of these two results if you're assuming that the features converge to the simplex ETF, which is a reasonable thing to assume since we've seen that in practice. That's it. Thank you very much. And I will remain for questions.
This isn't related to the lecture, but the other day when you sent us a video for the with Esther, I was just wondering, is there a relation with dressing up because of like the ball that she did?
I actually have no clue. I don't know. It's a good question. I also managed to find in the end, I was complaining how Toronto did not accommodate my religious snacks. But in the end, I managed to find a place that does sell the snack that you eat during Purim. So everything turned out to be nice and well. I'm not sure why people dress up. I mean,
Hey,
there's actually an interesting, how do you say it? I want to say it's not a rule, but it's kind of like a thing that's common, imposed on you during this holiday. I think it's one of the rules is that you have to drink a lot. It's actually a thing. So I think that the religion commands you to drink a lot, and people get extremely drunk on this holiday. It's one of those. It's an unusual thing to, to. It's not a rule. How do you say that? Like, it's not a commandment.
It's a custom.
A custom, yeah. It's very custom, yeah. So, yeah, Karen, I think I interrupted you.
Oh yeah, that's okay. I just I have a question about the slides on, they're called optimality.
Yes.
I didn't really understand. I didn't really understand the point or what was happening. I guess my confusion is, could you illustrate a pipeline of exactly like what the structure is we're dealing with? Like, we have a neural net, it seems, or we have some data coming in and out. Like,
yes.
I'm not sure I really get it.
Yes. Okay. Here's the idea. You have, this is all the layers of a neural net, except last layer. Okay. And you get as output the features which we're denoting by HIC, and you get as input XIC, right? Assume that this HIC is equal to mu C plus some noise. It's a generative model assumption. You assume that it follows some distribution, right? And then it goes into a classifier. The classifier predicts C hat, right? And you ask yourself, how could I obtain the optimal error? So in order to find the optimal error, you want to, let's say, maximize or I guess minimize, let's say minimize the probability of error, where what you're able to optimize over are the following quantities. You're able to optimize over the class means, the set of class means, the set of classifiers, and also the biases. So the class means are here, right? You can optimize over them. The classifier is here. Does this make sense? Now, the question here is, there's an implicit assumption here, which is that the network is able to generate any set of class means that you might want, right? It's kind of like you're threading. You can think of it as you have an over-parameterized network to a point where you can choose any class means that you want, but you cannot choose the exact features, so they still follow a Gaussian distribution.
When you say can't choose the exact features, would those features be the Zs or?
The features are HIC equal to mu C plus Z. I guess it should be ZIC.
Right, okay.
So it's like you have enough degrees of freedom to choose the class means, but you cannot actually pick the features. There's different ways of thinking about it. I like thinking about it as the network is over-parameterized enough to choose the class means, but the features are beyond your control. They're just hovering around the class means.
Right. Yeah. I guess if we didn't have that, it would be if we had that control, it would be a redundant problem, right?
Even under such case, you can prove that neural collapse would emerge. It's something that we'll discuss next lecture. So there's various settings you might consider, various mathematical theoretical setting, and you could ask yourself in each of these settings, is neural collapse emerging? And how close is this setting to the true setting in which neural collapse was first observed? So do you agree that this setting is not equivalent to the deep learning setting, right? Because you have access, you can optimize over class means, right? But in reality, there's a set of parameters theta that you can optimize those parameters. You cannot actually optimize the class means, right?
Right. Got it. Right, and that's exactly what you're doing on the following slides.
Yeah, and so the point is that if you optimize this, you can prove that the optimal means are equal to the optimal classifier transpose is equal to a simplex ETF. There's two settings you might consider. You might consider the setting where ZIC is normally distributed with a vanishing variance, or you might assume that the ZIC are L2 norm bounded, which is adversarial robustness. In one, sorry, go ahead.
Oh, do we assume that sigma is something that we get to optimize over as well?
No, sigma is vanishing to 0. So you're essentially asking yourself, in a case where I have a tiny probability of perturbation, the perturbation is extremely small, right? What would be the optimal classifiers and features? Why would it make sense to assume that the perturbation tends to 0? Because that's just NC1, activation collapse.
Right. Fair enough. Right. That makes sense.
So how do you optimize for the means? Like, do you use gradient descent or something else?
No, it's just a theoretical question at this point.
Oh, but are there any algorithms for doing this?
No.
Oh, okay.
Because no one ever, I'm not aware of anyone who calculated the class means of the features in the last layer. So there wouldn't be an algorithm that tries to optimize over them. But
Okay.
the idea is that by optimizing all the parameters in all the previous layers, you're inducing a dynamic on the last layer features. There's two things that can happen in optimization. Either you optimize something directly, or you're optimizing something it depends on, and then you're changing that thing indirectly.
And so you're trying to optimize the means through these theta?
Yeah, that's what's happening in practice. But theoretically, that's an impossible problem to tackle, right? Because it's a non-convex, high-dimensional, extremely complicated optimization. So what you can do is make a mental model, a simplification, where you just say, okay, imagine that I were able to choose the optimal class means, right? What would those class means look like?
So this is like a wild guess, but like, is it possible to just to change the input somehow?
Change
like,
the input to what?
Like embed them in some like low dimensional space to make the parameters better.
When you say parameters, do you mean theta?
Yeah.
You're saying, is it possible to embed the theta parameters to make them use C's in a low dimensional space? Is that what you're asking?
I mean, like you said, this was a very hard problem. Like, but instead of like changing thetas, can you try changing the inputs?
Mathematically, you can. It's a problem that that's what we're doing, right? We're changing the mu's instead of the thetas.
Oh, I meant like the XIC.
Oh, the XICs are fixed because that's your training data.
Oh, okay. Yeah. Okay, thanks.
Professor?
Mm-hmm.
So I have a question about the general flow of the analysis here. So we started by looking at the empirical evidence that these MCs, they occur.
Yeah.
And then there's some of them that's a bit sketchy, but it's okay. 95% are all demonstrating that. And then we like, instead of proving that, for example, all of them occurs, but what we're doing is we're studying the connections between them. So for example, we assume one or two of them, and then we prove another one.
Yeah, that's what was done here.
I see.
Let's say here. Yeah.
Okay, sounds good.
But there's different approaches to trying to understand neural collapse. One of them is by assuming certain properties of neural collapse and then showing that previous results, result in neural collapse, right? That's what you just said. But an alternative thing you could do is just try and prove that neural collapse emerges without making assumptions about the features of classifiers, right? And that's something that I'll show in the next lecture.
I see. Sounds good. Also, just an offhand comment that one of my friends has become your YouTube fan.
Oh, yeah?
Yes.
Is that person in the course or just in general?
No, she's outside the course, but she's just watching your video and smashing like button.
Oh, yeah? Wow. Is it because of the educational content or because of other reasons?
No, because I sent her the pictures that were generated by the algorithms, and then she started watching your videos to learn about what the hell these happened.
I see. That's cool.
Professor, I think the next level is to do Deep Dream on your actual background and then put that as your Zoom background,
I think that's a beautiful idea, but I don't know how to do it. I think it might be complicated. I think Zoom should do it. Maybe you should send them an email.
I have two questions. Can I ask?
Yeah.
First is about NC properties. As you mentioned, I think NC1 to NC3 are self-consistent, that you can derive NC4 from those first three, yeah?
Yeah.
And NC1 and NC2 are sufficient conditions for all of the theorems.
Which
we
one?
don't need-
NC1 and 2, you said?
Yeah.
Yes, that is correct.
For neural collapse to happen.
Yeah. But ideally, you would want to prove neural collapse happens without assuming that the features are the simplex ETF.
Mhm.
Because that's
Yeah.
kind of too strong of an assumption, I would say.
Yeah.
But it's nice in terms of the flow of the course to say that, you know, we've seen the max margin classifier, we've seen this non-linear discriminant analysis, and we've seen neural collapse. What's the relation? The relation is that neural collapse is a special case of the previous two, which is the case that is of interest because it emerges in deep nets.
And both of them should happen simultaneously for us to see neural collapse, yeah? I mean, NC1 and NC2. I mean, only NC2 is not sufficient for neural collapse to occur.
So ideally, you would like to say that if I do like, you know, ideally you would want to say that if you optimize some loss function, then neural collapse occurs without assuming anything. So you wouldn't want to assume NC1, NC2, NC3. You would just want to prove everything.
Oh, okay.
Ideally.
Okay, yeah, I see. And I have another question that what is the origin of this neural collapse? I mean, for the first time, who and when who discovered this phenomenon and when it was?
So my co-authors and I did that around the summer.
Okay.
This summer. Lots of times during COVID.
And all of that is contained in your this paper, prevalence of neural collapse during the terminal phase of deep learning training, yeah?
Not everything, but most of it. For example, this
that was the only paper I found in your Google Scholar that was on this neural collapse.
Yeah, that is correct. Yes. But some of the things I'm showing here did not appear in the paper.
Oh, okay.
Like this plot.
And I searched through the references and I didn't see any information theory paper except the Shannon's paper.
Yeah.
And I mean, since this is a new topic, I'm just asking, there were some relations between information theory, and you defined some notations during the lecture that I couldn't see in the paper. I mean, I think they were delayed the slides only because of the clarity, yeah?
Which notations?
Those linear coding over.
Oh, it's in the appendix. There is an appendix.
I can't see, I think. Maybe the version I'm seeing right now doesn't have any appendix.
Okay, so 1 second, I can send it.
So is it the first paper that is talking about a neural collapse phenomena in deep networks?
Yes. I find this surprising.
Yeah, because I think at least empirically they can observe many people are working on these topics, and at least empirically they can discover this phenomena that the in-class covariance diminishes, or these centers become concentrated, or
Yeah.
I mean, it's surprising that nobody else discovered it.
Yeah.